In this video I will discuss something about the flexural strength equation. So in the previous video you saw this equation, how we derive this, but there is some more discussion needed for this equation. uh, yeah, before that, so I should define another parameter, that is rho. So what is rho? You can see our rho here. So rho is the still ratio. So rho is the still ratio. So rho is area of steel divided by BD. Now the uh, intersection is represented by BD, not BH, because okay, why? So if this is my reinforced section, this portion is D and this is B. Now this portion, anything below the reinforcement, is just cover. So this portion is just cover for the reinforcement. It doesn't do anything structurally. So our main section is B times D. That means this area, and it is only for beam. Again, for column there is different steel ratio. So for beam, by steel ratio we mean area of reinforcement divided by the cross section, and cross section is represented by B and D. That is the steel ratio. Now if you go back to uh, so what we learn, then rho is ASBD, or AS is rho BD. So we can replace AS by rho BD. So if I go back to book again, so here AS we can replace it by rho BD, and then DA. Now we can again replace A. How can we replace A? So you know that A is AS, FY 0.85 A prime CB. Now if I replace AS by rho BD, then there is a new term. New term means A will be in defined way. There will be no AS, there will be rho BD. So if we replace A, if I go back to the book, if I replace this, then I will get this equation. So I am replacing AS and A, then my equation is becoming this. Now in this equation you can see here rho Fy1 minus rho Fy 1.7 FMC, this portion. So this portion is completely material properties, nothing to deal with the design. So design is rho BD is here. My design is BD square. What will be my width? What will be my depth? Excuse me. So I believe that you didn't understand what I mean. I mean that only this portion. So only here. It's not going. Or if I write it down, so if I write it down, this equation in a defined way, where I will place it, say maybe here. So if I write it down, I can write this way: EMU over phi B D square equals so equals Fy rho 1 minus rho Fy 1.7 F prime C. So if I write that this equation this way, so you can see that this portion is completely material properties. If I know the strength of concrete and the yield strength of steel, then, and if I know my rho, what the rho I am using, then I can find a value, that is this value. Now it is very helpful when we will design the beam, you will see. So for now just remember this, that many book give the value of this. You do not need to calculate it. If you know your Fy and F prime C, many book will give you. So I am showing you here this book. So in this book Now if we use other book, no problem, almost all books give this value. In your book, say here this one, table 8 in this book. So depending on row, mu over pbt square, that means that calculation that calculation they gave here. So you do not need to calculate it. So we will use this depending on my fy and f prime c. Define fy, define table. So make sure that you are familiar with this, where it is coming. Okay, then another concept I need to discuss before designing beam, and that is balanced steel ratio. So balance steel ratio, what is this? Balance steel ratio. Balance steel ratio is the ratio at which my concrete will fail and steel will yield at the same time. So that is called balanced steel ratio. It is a theoretical value because it is very difficult to obtain this combination. That means if this is my reinforced section, so um, so this concrete will fail and the steel will yield fy at the same time. So which is very rare. But and now what will happen if my reinforcement is less than balance? If my reinforcement is less than balance, that means it will go up. My stress here will go up and my stress here will go down. If it goes down, then that means it is good. So my concrete will be in good shape, but my steel will yield whatever we want. So it is better my reinforcement is less than the balance. What will happen if my steel is more than the balance? If my steel ratio is more than the balance ratio, what will happen? Then this will not yield, but this will fail. So concrete will fail and steel will not yield for this case, which is bad, because we do not want concrete to fail, because concrete failure is sudden. But and what about if row is row B? Perfect, no problem. This will fail and this will yield. Concrete steel will yield. That is good. And what about if my row is less than row B? There, that means this will yield for sure and this will not fail. Not fail. That is better. So at least we should stay here. We should not make our reinforcement more than balance. At least equal, but equal we cannot maintain. If it goes little higher, then you will not satisfy this. So better not to do this. This is the best option. Always make your steel ratio less than balance. Now how, we will see when we will design the beam. But now I am showing you. Now here your book is showing how to derive the amount of balance steel ratio. You know that from this strain diagram, you can, from similar angle triangle, you can write this equation. In this equation they are inserting the value of a. So value of a and c they are inserting, and then they are getting this equation. Now I am not deriving here because it's very basic equation. Anybody or any book will show you this, but I am showing the concept. Actually we do not use this equation. Nowadays we do not calculate it. Everything is given in the appendix of any book. So but we need this concept that our steel ratio cannot be balanced. If it is balanced, then I am at the boundary. If my ratio is more than balance, then my concrete will fail. So that is bad. So my steel ratio should be less than this. So this is another concept. Other concept we need is minimum amount of reinforcement. I don't know why it is in your book. So minimum amount of reinforcement here. Yes, so these two equation. Why do we need to provide minimum amount of reinforcement? The answer is here. So minimum. So yes, this reinforcement I must provide some minimum for flexural. Why minimum? Because I should make sure that the strength of this steel is greater than this. Otherwise what will happen if there is a crack here? Because we know that concrete will fail. If there is a crack here, this will fail also. if its strength is less. But if its strength is higher, if there is a crack, my reinforcement will be there. This is why I need to provide minimum amount of flexural reinforcement. We call it minimum, yes, minimum for flexure. Why do we provide? To make my steel strength greater than my concrete strength. That is why we need to provide it. How much it is? ACI gave us this value 3 root over f prime c fy times BWT. Now this BW means actually B. BW means actually B. BW means like actually this width, and T means here to here. Compression phase to the center of the reinforcement is D. Okay, so hopefully you learned the minimum or not less than this. So to ACI gave us two equation. We must provide this amount of reinforcement. There is another concept. Another concept of minimum reinforcement is that not about flexural. I must provide some reinforcement for temperature, and that reinforcement is not as much as this, slightly less than this, and typically that reinforcement is not a control factor in beam. It is a control factor in slab, because in slab we need so minimum amount of reinforcement that sometimes my required reinforcement is less than the temperature. We cannot provide that. So if I give you the summary, this reinforcement must be greater than temperature for slab. This reinforcement must be greater than the minimum for concrete cracking. Okay, so hopefully you understood now. So when we will design it, we may need this concept. That time if you ask, then I have to explain. Better I am explaining before that. Now if I go back to your book to see some table, yes, this table is very helpful to choose my reinforcement. You can see it. So this table is table A7. Say for A prime C 4000, and say our reinforcement is still 60 grade. 60 grade means yield is a 60 KSI. I have different values, or go close to the go here, maybe very close to discuss it. Say for our concrete is 10, sorry, concrete is 10 3 KSI and steel is 10 40 PSI. There are lot of reinforcement ratio. Row balance, where it is, now you know where this is coming. Row balance, they calculated based on that equation that I showed in the book beginning. Row when epsilon t is 0.004, you know that our epsilon t should not be less than 0.005, but designer says if it is 0.004, that is okay, but 0.005 is the best. So if you want to make your epsilon t 004, choose this ratio. If you think no, I will maintain this, the based on, and that is economical also, because my reinforcement will decrease. See, 0.0232 0.0203, so this is less. If you want no, I want to provide even less reinforcement, where epsilon t is 0.0075, you can provide that. So best is to provide this one, and you can provide this one to make it even more economical, but you must provide this amount of reinforcement. It is minimum for flexure. Where I found it, I just discussed that I must provide more than the requirement for the concrete cracking. So I need to provide more than that. So you cannot provide less than this anyway. Best way to provide this, and this is your boundary. If you go above this, your concrete will fail, steel will not. So this table is very helpful to understand or to choose your reinforcement ratio directly. Okay, so hopefully I discussed the some other discussion we need for our designing. Something else maybe in the next chapter. You can see here rho mean for temperature and shrinkage. So for this strength of concrete and this strength of steel, we cannot provide less than this for our temperature. Is not for the flexure. Flexure little higher. If I go, maybe I missed it. say minimum for flexure is 0.005, minimum for temperature is 0.002. So if you design for beam, you must provide this amount of reinforcement. For slab, you must provide this amount of reinforcement. Okay, even for temperature, you can never provide reinforcement less than the temperature. Temperature is the minimum you must provide, but that will not take any load. To take any load or flexural, you must provide this. So hopefully you understood the some other knowledge is required for the reinforced concrete beam design. In the next slide, we will start the design. Thank you.